Welcome to this session on electron configuration. In this video session, we will be learning about certain rules which helps us to determine the location, the orbitals, the shells of an electron in an atom. And at the same time, we also talk about certain anomalies that can be seen with respect to electron configuration. Why should we know about the quantum numbers or the arrangement of electrons? It is because once we are thorough with knowing how the electrons are arranged, we can predict a lot of things about an element, an atom, and the compounds that it would form. It helps us to know about the periodic table and thereby helps us to study about the compounds that it would form. Also, it will give an insight on how many electrons are present in the core of an atom and how many electrons are present on the outermost shells, which are called as the valence shells. Knowing the number of core electrons and knowing the number of the valence electrons is very important to know more about an atom. For example, if I want to know about an ionization energy, it is very important to know about the valence electrons and also the number of the core electrons an atom has. It is also very much helpful in computational chemistry because this helps us to kind of qualitatively estimate the chemical properties of an atom. To understand and interpret any atomic spectra, again, we take the help of electron configuration, and it will also help to determine the number of electrons in the ground state and the excited state, which is a prerequisite to study about many kinds of spectra, inferential studies, and so on. So moving further, let's talk about certain rules that are followed by the electrons when filling up the shells of an atom. The first principle which is followed by the electrons is something that we call as the Paulis exclusion principle. The principle which we have already come across in our previous video. It states that in an atom or a molecule, we cannot find any two electrons having the same 4 electronic quantum numbers. If by chance you see the principal quantum number, everything the same, at least one quantum number, which happens to be the spin quantum number, will be different. Let's study that with an example. So consider an atom here with a nucleus and having 2 electrons. Let me say this is the first electron and this is the second electron. If you look at these 2 electrons carefully, you see that there are at least 3 quantum numbers which are the same. They are in the same shell, so their principal quantum number is the same, right? Its azimuthal quantum number is also the same. Because we are talking about the 2 electrons in the first shell, their magnetic quantum number is also the same. The last quantum number is the spin quantum number, and you see that the spin quantum number of these 2 electrons, the electron 1 and electron 2, will be always different. If one of the electrons has a plus spin quantum number, the other one will have a minus spin quantum number. So you can see in the first shell, the 2 electrons will have these 3 quantum numbers the same, but the last one will be different. So no 2 electrons will be having the same quantum numbers at any given point of time in an atom or a molecule. Now this is Pauli's exclusion principle. The second rule is something which tells us about the number of electrons that can be present in an orbital. So if you're talking about the first orbital, you see the first shell will have only one orbital, which is 1s, right? And this 1s can occupy only 2 electrons. Let's talk about the second shell. The second shell will have 2 subshells. One is 2s and the other one is 2p. Now 2s will occupy 2 electrons, but when we talk about 2p here, you see that this can exist in 3 different orientations: 2px, 2py and 2pz. Now looking carefully, you see 2s can occupy 2 electrons, 2px can occupy 2 electrons, 2py can occupy 2 electrons and 2pz can occupy 2 electrons. So basically we have 8 electrons that can fill in the second shell. Talking about the third shell, which is 3s. 3s can occupy 2 electrons here, 3p which can occupy 6 electrons, and talking about the 3d, you see that 3d can exist in 5 different shapes, and because it is 5 different shapes, you can see each orbital can occupy 2 electrons each, and therefore it can occupy 10 electrons. Therefore, the total number of electrons in the third shell would be 2 from s orbital, 6 from p orbital and 10 from the d orbital there, and totally we have 18 electrons. So that way each orbital can occupy a maximum of 2 electrons and each shell can occupy a maximum of 2n square number of electrons. So in this fourth shell, you can see that it can occupy 32 electrons. Yes, so that is a basic rule again that we see for electrons to occupy in an atom. Let's go further and talk about one more rule that is followed by the electrons, which is called as the Hund's rule of maximum multiplicity. Now, Hund's rule of maximum multiplicity states that every orbital in a sublevel is always singly occupied, okay, before they are doubly occupied, and they generally will be occupied with the same spin initially when they are singly occupied to have the maximum total spin. Let us see what exactly it means. So in the case of the first shell, we have 1s. So there is one electron, let me say, which is having a positive spin. I will denote it like this. Now the second electron which is going to be filled will come here in the first shell and occupy this way, right? So this is what we call as the filling of the 1s orbital. Now after 1s gets filled with 2 electrons, it goes to the second shell. Again, where you see that there is one electron that gets filled here with a positive spin, and then there is a negative pinned electron that would occupy the 2s orbital. But in our second shell, there is also 2p, right? There is also 2p, and as we have seen, 2p will have 3 orientations. One is 2px, the other one is 2py, and the other one is 2pz in 3 different orientations. Now we have already seen that 2p can hold around 6 electrons. The first electron goes to the 2px. Now second electron, instead of getting filled in the 2px itself, goes to 2py, and please note that it is also having the same spin as the electron having 2px. Then the third electron goes and occupies the 2pz here. Now all these 3 electrons are singly occupying the subshells or the different sublevels, right? Now these 3 orbitals, the 2px, 2py and 2pz, will have similar energies, and we will also call them as the degenerate shells. We also call them as the degenerate shells. Now what happens to the fourth electron? Now the fourth electron would go and occupy 2px and would have the opposite spin. The fifth electron would occupy the 2py, and the sixth electron would occupy the 2pz. Please note, this x, y and z orientations are something which we are kind of giving a reference to so as to understand it much better. Moving to the third shell, we have 3s again here. Now 3s would be filled first with 1 electron, the second electron, then comes the 6 electrons that would get filled here, right? And you see that the same order is followed, and when we are talking about the d orbital, we will have not 3 sublevels, but we will have 5 sublevels, because the d orbital has 5 different orientations that it can take. Now, amongst these, the first 5 electrons would occupy the d orbital shells. They are half filled right now and give stability to the atom, and only the 6th electron filling up the d orbital, you see, goes to the same shell. So this way you see that every orbital in a sublevel is always singly occupied before any orbital is doubly occupied, and you see that they all have the same spin, so that the total spin is at the maximum level. Now let's go to understand one more rule, a very important rule, which is called as the Aufbau principle. Aufbau means construction or building up. Aufbau basically means in construction, or we can say it is building up. Now just imagine that I have a nucleus, right? And there are absolutely no electrons. Please note, this is a hypothetical situation. I just have a nucleus having many protons, and just imagine that I am going to leave electrons into this particular positively charged proton. Now, when I leave these electrons, you see always the lowest energy shells are the ones which gets filled first. Always. So you see that we have this white colored line that is showing us the first shell, n is equal to 1. The principal quantum number is 1 here, and you see that it can occupy 2 electrons. Now suppose I give the third electron there. The third electron cannot fit in the first shell. Why? Because the maximum number of electrons that can fill in first 1s is always 2. And if by chance I put one more electron in 1s, there would be more of electron repulsion that would happen, and such an atom would not be stable. The electron is automatically pushed to the second shell. The second shell is farther from the nucleus and has a higher energy when compared to the 1s. So the second shell will occupy 2 electrons. Now after 2s gets filled, then it is the p orbital that should get filled, and we have seen that the p orbital has a shape of a dumbbell, and which can exist in 3 different orientations, the px, py and the pz, and the next shells that would get filled is this p orbital. As you can see in the picture, px, py, pz will have a very much similar energy, right? Very close to 2s, however slightly higher than 2p. In fact, that is the reason why if an electron has to choose between 2s and 2p, it is always the 2s that gets filled first and then the 2p. And 2p can occupy how many electrons? 6 electrons. 2px, 2py and then the 2pz. Yes, so basically right now we would have 8 electrons that are filled in the second shell and 2 electrons in the 1s shell. Now if at all there are more protons and my atom can take in much more electrons, only after the 2s gets filled and the 2p gets filled, then the electrons will go to the third shell, which is the 3s. Now 3s can occupy 2 electrons. Why 2 electrons? Because s orbital can occupy 2 electrons. After s orbital is filled with 2 electrons in the third shell, then it has to be the 3p, right? Now 3p, there are again 6 electrons that it can accommodate. Now as per our understanding, it should be the 3d that should get filled, right? But in reality, that does not happen. Instead of 3p, we see that it is the 4s that gets filled. Now you might ask, why is that 4s gets filled before 3d? It is because the 4s and 3d have very much similar energy levels, and 4s has slightly lower energy when compared to 3d. So after 3p gets filled, it is 4s that gets filled, and after 4s gets filled, it is the 3d. So 4s is filled with 2 electrons, and later 3d is filled with 10 electrons. So that way you see the electrons always occupy the lower energy shells first. Okay, so how am I going to remember this? Which shell would have how much energy and so on. Now for that we have a very simple way of representing them on a block diagram. So let us see what it is. So we can write it like this here. So this one would be the 1s, this one would be the second shell. I will just write it as 2s here, and this would be 2p, right? Now this would be 3s. Now this would be 3p, and we know third shell will also have 3d. Then we have 4s, then we have 4p, 4d and 4f. Then we have 5s, 5p, 5d and 5f. Similarly, we have 6s, 6p, 6d and 6f, 7s, 7p, 7d and 7f. Now if we want to know how the electrons are filled, it is very easy. We can start filling up our electrons from 1s, moving from our right hand top corner to left hand bottom. So always it is the 1s that gets filled. Then comes our 2s, 1s, 2s. After 2s it is 2p. After 2p it is 3s. After 3s it is 3p, and then the 4s. After 4s it is 3d, then 4p and then the 5s, and after 5s gets filled, it is 4d, 5p and 6s and so on. So this way, if I just write these blocks, the blocks each one representing the number of shells of an atom, the subshells of an atom, and I keep writing this arrow mark, I get the arrangement of electrons in an order, right? So this is how Aufbau principle tells us that the lower energy shells are occupied first, right? Now let us talk about certain examples talking about all these principles that we have learned till now. So let's start with hydrogen. Hydrogen is having only one electron, and therefore you see that it occupies 1s, its electronic configuration is 1s1, so it has only one shell and with only one spinned electron. If we are talking about helium, helium has 2 electrons. It is not that it has 2 electrons like this, one in 1s and the other one in 2s. It is not that there is one electron here and one electron here. Now this will not happen, right? Always you see the first shell, the lower energy shell is 1s, and this has to get filled with 2 electrons. So 1s2, right? And let us talk about nitrogen. Nitrogen has 7 electrons, right? Now let us start writing the 7 electrons in an order. So it will have 1s, then it will have 2s, and then it will have, I am going to write p in one single box so that it is easy for us to understand. So this would be 2p, 7 electrons. 1s gets filled with 2 electrons initially. 2s also gets filled with 2 electrons, and let us fill up with the 2p orbitals. 2p orbitals, you see 1 electron gets filled here in 2px, 2py and 2pz. Please note that 2 electrons will not fill 2px based on the Hund's rule that we just discussed. So this electronic configuration would be 1s2, 2s2 and 2p3. Talking about oxygen, oxygen has 8 electrons, where you have 1s completely filled, 2s also completely filled, and 2px will have 2 electrons, 2py will have 1 electron, and 2pz will have 1 more electron, which I can simplify and write it as 1s2, 2s2 and 2p4, right? So that is the electron configuration of oxygen. Let us see what would happen in the case of fluorine. Fluorine would have 9 electrons, right? It would have 9 electrons, and when we're talking about 9 electrons, 1s is completely filled, 2s is also completely filled, 2px will have 2 electrons, 2py will also have 2 electrons, whereas 2pz will have only 1 electron, right? Now I can simplify this and write it as 1s2, 2s2 and 2p5, right? Now let's go to another element, which is neon. Neon has electron configuration of noble gas. So basically it should have 10 electrons, and you see that 1s2 is completely filled, 2s2 is also completely filled, 2px is filled with 2 electrons, 2py orbital is filled with 2 electrons, and 2pz is also filled with 2 electrons, and therefore to summarize I can write the electronic configuration as 1s2, 2s2 and 2p6. Now you see that since the electrons are completely filled in the second orbital, this neon does not participate in many reactions and is kind of chemically inert, hence the name the noble gas. Now is it that we write the electron configurations only for the first few elements? No, not necessary. Let us just take the example of krypton. Now this krypton has got 36 electrons, okay, 36 electrons. Now this 36 electrons are arranged like this. So 1s2, 2s2, in its p orbital 2p6, all of them are filled. Then we write 3s2, 3p6, then 3d should get filled, but that does not happen because 4s has lesser energy, so 4s2 gets filled. Then comes our 3d 10 electrons. After 4s 3d gets filled, and after 3d it is the 4p electrons. So let us do one thing now. Let us count all the electrons that are present in each of these shells and the subshells. Did you do that? Yes. So totally we have 36 electrons that are present in different shells and the sublevels, as it can be seen. Also, you see how well 4s2 gets filled before 3d10, and this is something which we are always interested in because it kind of tells us where our valence electrons are. Looking at this kind of complex electron configuration, you will also see that these electrons which are here are somewhere inside the atom, closer to the nucleus. We call them as the core electrons, and the one which is in the outermost orbital, we call them as the valence electrons. These valence electrons are very important for us to know more about our elements. So these are some of the electron configuration examples of few elements. I would want you people to pause the video at this point of time, randomly take few elements and write their electron configuration, applying all the rules that you have just learned. You might be wondering if electron configuration is something which is very standard and is very important for us to know everything about an atom. Yes, in many cases, but not in all the cases. Let me just give you two important anomalies that can be seen. Of course, we will not be dealing this in detail because we'll be learning these when we are learning more about our transition metals and so on. Though we are talking about electron configuration and how helpful it is for us to understand about an element, you sometimes see certain anomalies. For example, if you're talking about the elements from, say, scandium to zinc, you see that the electron configuration is not as constant as we discussed till now. There is some kind of rule that gets slightly changed, and hence the same rules that we just discussed right now will not be good enough to discuss the electron configurations of scandium to zinc. Similarly, if you're talking about the electronic configurations of, say, chromium and copper, you have a electron configuration, but you will realize very soon when we talk about these elements in particular that the electron configurations are not something which is very stable for chromium copper. There are certain elements which shows multiple valencies, and therefore the electron configurations also changes. And with certain anomalies also, understanding electron configuration is something which is very, very important, because this is going to pave a way for us to understand more about electron, element, bonding, compounds and molecules. Thank you.